for giving your time and everything and coming here and explaining everything to us. So yeah, we thank you very much for that.
No problem.
And so maybe we start. So good afternoon, everybody. Welcome to the SP webinar on carbon capture and storage. We welcome you all. I welcome you all on the behalf of SP Aachen University Student Chapter. So today's webinar would be focusing on carbon capture and storage. So like that everybody knows. So that's the reason why everybody are here. So the video is recorded and it would be uploaded on YouTube later. So first of all, I would like to invite and introduce our speaker, Melianna Ulfah. She's an M.Sc student from Indonesia and currently works at Tetra Tech. Currently, she's working and assisting for the development of carbon capture, utilization, and storage projects. In the initial phases of her career, she worked in the energy industry as a geophysicist for assessing the pre-drilling geohazard risks in offshore oil fields. So throughout, like through her master thesis, she delivered policy recommendations to Texas General Land Office based on experimental research in geosciences and reservoir characterizations and simulations. So this is that she did it in order to optimize the CCS operations. During her fellowship at the Lawrence Livermore National Laboratory, she helped characterize the CO2 storage in the Northern California and calculated the static storage capacity of the depleted gas fields. And she's currently assisting energy companies to accelerate the CCS projects. And that itself plays a major role in decarbonizing the oil and gas industries in partnership with Tetra Tech. So she's very passionate about championing equitable, science-driven, and ambitious climate solutions. So again, as you all know, she'd be giving a talk about reservoir modeling, simulations, and assessment of carbon capture, storage, and utilization. So this whole webinar would cover the introduction to the technique and later would deal with the physical and let's say geological aspects of the whole technology. So like as everybody know we would first let the speaker complete her talk and you could start posting your questions in the chat, or maybe afterwards we can just you can raise your hand and ask the questions yourself. So thank you very much for now.
I guess I will start sharing my screen and get started. Oh, I can't share my screen.
I think you can
try now.
Okay, let's see. All right, everyone can see my screen, okay?
Yep.
Okay. So yeah, thanks for the introduction, Aditya. So as mentioned, I'll be talking about basically the modeling simulation, and I'll be sharing some of my past projects that I can share. But I would like to start my talk so that we all are in the same page. So I just snip a couple slides about basically the basics of CCS. And if anyone is already familiar with CCUS, I hope I'm not telling you like the same thing over and over again. So yeah, let's start with a question about what is carbon capture and storage. So from its name, capture, so the process starts from capturing the CO2, and it can be from lots of things. It can be from the CO2 as a part of electricity generation. If it's from natural gas or from coal, it can also be from the processing of the biofuel. And it can also be from direct air capture. It can also be from gas processing plants like the Sleipner project in Norway. That's the first CCS project in the world actually for like carbon sequestration, not for EOR. And lastly, it can also be from the CO2 from the electricity generation from geothermal. That's the Carbfix is doing in Iceland. And so after we're capturing them, we usually ship the CO2 from pipelines or from trucks, depending on the quantity and depending on the distance between the source and the sink. And then we inject them back into the subsurface. Why back? Because most of the CO2 or like the carbon that we capture is coming from the fossil fuel and it's from the subsurface. And there are several options to store CO2. It can be from the depleted oil and gas reservoirs. It can also be for enhanced oil recovery. That's actually the very first use of carbon capture and storage. It can also be from the saline aquifer that's deep in the subsurface. That's not for like water use, and can also be from unminable coal seams or enhancing the coal bed methane recovery. And lastly, like what Carbfix is doing to other kind of rocks such as basalt. And so as a geoscientist working in carbon capture and storage, I often being asked, why storing the CO2 underground? Why not catapulting it out of the earth, like to the space? And the reason is because, as far as I know, such technology does not exist yet, but we know that injecting something into the underground, we have the technology, and it emerged from the oil and gas industry. And as I say, the very first CO2 storage project is CO2 EOR, and it dates back to 1972 in Sackrock Field in West Texas, and it's a CO2 EOR. So right now it's 2022, so we can say that the technology has been around for like 50 years, so we can say that it's a mature technology that we can trust, and we can keep developing over and over again to like ensure the safety and the very long terms of like keeping the CO2 in the subsurface. And again, because of its close ties to oil and gas industry, to oil and gas exploration and production, there's so many adaptable concepts from oil and gas exploration and production that we can adopt for CO2 storage. It's as simple as the concept of using reservoir as the house for the CO2, the concept of looking for such structure equipped with the seal to keep the CO2 underground, just like what we've been doing in oil and gas exploration. Like we want to find a reservoir with the seal because we want to make sure that the oil is still there, not escaping anywhere. And there are also other concepts that I will share later. It has something to do with my study, that is oil migration concepts. But before we're going through there, again, because of the close ties of the oil and gas industry, the reason why we're storing CO2 underground is because there's an opportunity to reuse the facilities. As we know that we want to reach carbon neutral. So many countries are having these carbon neutral goals, and the most prominent action that they're doing is to produce more and more energy from renewable energy. And so we're going to see lots of oil and gas fields being being closed, like stop operating oil and gas industry, like less operating oil and gas industry. And so we're going to see more and more oil and gas facilities being decommissioned. And so it's going to be much better if we can reuse those facilities for like storing CO2. That would be as part of an effort for carbon removal, because again, in approaching or like to accomplish carbon neutral is not just CO2, reducing the CO2, but also, I mean, it's not only reducing the CO2 by producing energy from renewable energy, but we also need carbon removal. Yeah, so yeah, not just carbon reduction, but we also need carbon removal, such as CO2 storage. So again, the question that I get asked often is that how can the CO2 be stored underground? I get some questions such as why, what if it gets exploded, like it's a gas and it's like in the underground, what about the pressure, blah, blah, blah. And so the first thing that we as a geoscientist to consider when choosing a layer of geology to store CO2 is this window between the supercritical window, the supercritical upper boundary and the upper boundary is the supercritical line, and the lower boundary is the overpressure. For the overpressure, I guess it's intuitively explained, like we don't want to inject the CO2 deep enough that the pressure is really high and it's gonna cause like seismic activity, and it's going to reactivate fault and making surface uplift, etc. But we also need to store the CO2 below the supercritical limit. So what it means by supercritical is that it's a condition where it has certain pressure. I believe it's around 70 bar, and a certain temperature too. The minimum temperature is like 30 degrees Celsius. So above that pressure and temperature, CO2 is in the supercritical state, which means that it has a density close to a liquid, which means that it will need much less space to occupy than when the CO2 is on the condition up in here on the surface. So it needs much less space, but even with that density, it still behaves like a gas, which means it moves more freely than liquid. So it's really it has something to do with the miscibility, with the trapping, with the reaction with the brine or any kind of reservoir fluid that we're going to inject the CO2 into. I explained about how can the CO2 be injected, and now how can we be sure that the CO2 stays there. So there are multiple mechanisms that happens when you inject the CO2 into the subsurface. The first one is the structural trap. So as I mentioned, the concept of reservoir and seal. So you want to inject the CO2 at the reservoir, and then it keeps migrating outwards because of the buoyancy, because of the nature of the CO2 as the gas. And so it will reach the seal, but like the seal is very impermeable, and so there's not much enough capillary pressure for the CO2 to go through the seal, and so it's just being structurally trapped. But other than that, actually we can also, what happens is also a residual trapping, and it does not necessarily happen, and it does not the structural trapping does not necessarily have to happen in order for the residual trapping to happen, because it happens when the CO2 is traveling, is migrating from like the well into like the structural trap itself. So as you can see, we inject the CO2 in the reservoir. There are already fluids in there, whether it's brine, whether it's a saline aquifer, which actually is the same thing. And so while the CO2 travels through the pore space and the brine, some of the CO2 get left in between the pore space and the brine, while like the most fraction of the CO2 keep flowing, and some of them being residually trapped along the way, and until finally they got structurally trapped under the seal. And so this residual trapping is really, really helpful to get the CO2 into the next phase, that is solubility trapping. So when the CO2 is in the phase of solubility trapping, it's just like soda, it's just like Coke. You don't really see bubbles within the fluids. It's just all fluids, but it actually has CO2 in it unless you shake it, and it brings it, like it gives us pressure, and it makes the CO2 visible. But when we're injecting the CO2 in a calm environment, that's why we also assess to inject the CO2 in an area where it's not so much seismically active, so we can keep this we can like make the CO2, like the journey of the CO2 to get permanently trapped will be as smooth as possible. And the next thing that happened after solubility trapping is a mineral trapping. I can say this is the next step when it comes to injecting CO2 in a siliciclastic sediment such as sandstone, and it can happen in a scale of thousands of years, because when it comes to mineral trapping, it has something to do with the chemical reaction within the CO2 and the kind of rocks that we're injecting into. And it can be different, of course, from rocks to rocks. Like I said, in sedimentary rocks, it can happen in a scale of thousands of years. But if you're injecting CO2 into I'm not sure about carbonates, but in basalt, like what Carbfix is doing, the mineral trapping can happen as fast as in less than a year. And it's because of the reaction between the CO2 and the basalt. So yeah, now we are entering into the topics where it's mentioned in the title of the event, that is modeling. So the first thing that we do as a geoscientist to model, to create the geologic model for CO2 storage, is to shop for data. And at a minimum, we should have a well of data to like correlate the formations and make to also look up your depositional history and for you to pick which horizon or which formations would be suitable for CO2 storage, and to see if this seal is good enough to hold the CO2 underground, etc. And then we're going to need seismic data, because up until now, seismic is still the best data that has a best quality and also resolution when it comes to like assessing the continuity of a formation. And also we can also play with attributes, and we can play with attributes, we can do inversion, we can make porosity model out of it, if of course if we have the well-locked data where we can have the physical properties that we can calculate, such as porosity or permeability. And it's also good to have core data first, of course, to maybe to conduct this core flooding experiment, so that you can calculate, you can acquire the permeability data, what's the permeability from that area directly, even though you can also use some formulas to calculate the permeability if you calculate the porosity from the well data. Also from the core data, you can also kind of see the pattern of the depositional environment, because everything is in fractal in geology. So you can kind of see, maybe you look up in your literature that what's the depositional environment, what's the azimuth, when is the arch of the deposition, the deposition, and so you can know it will. So if you have a facious model, basically it will be very helpful for you to make strategy on where to inject the CO2, and it will also depict the fluid migration in the modeling if you use facious modeling, and it's from the core data could be really helpful in building that. And also good to have the fluid samples from the reservoir. So in CO2 storage and in drilling in general, there's this thing called mechanical integrity testing. And so basically one of the components to that testing is to test whether the cement will be enough to hold, for the fluid to not get through the well from the cement itself. So you can kind of do some experiment how the CO2 reacts with the fluid, and if the cement is, if the interaction between the CO2 and the fluid will not compromise the integrity of the cement, so that it wouldn't cause any leakage, etc. And as I mentioned, there are so many options to store CO2. And if you're doing CO2 storage for the CO2 EUR purpose, of course, you will really need to have a pressure data, especially if the field is running. So it's going to be easier for you to have the pressure data. It's going to help you to like set up the simulation and set up the injectivity so that it won't reach the overpressure. And also, again, if it's in a CO2 EOR, it will let you know when to inject the CO2, when to inject the water to drive the CO2 that's going to be miscible with the oil. And of course, for CO2 for a sequestration purpose, for CO2 sequestration for permanent sequestration, it will be very helpful for you to like track the pressure for the simulation, so that again, to not cross the overpressure and make the operation as safe as possible. And so let's say that we've got the geologic model, but it's not, and it doesn't end there. So let's say from the well-locked data, from the seismic and the well-locked data, you only have horizons, you only have this that's a formation. The next thing that you do is, as I mentioned before, is to populate it facies. I think lots of modeling softwares has the capability to do this. It's pretty easy as from my experience, but the hardest part of generating facies model is how can you bring up the information that you get from all of the history of the geologic area that you're targeting into to your model, so that it can be as realistic as possible. And then from the facies model, we're populating the porosity values that we calculated from the well data. And again, if we're only using porosity model, usually it's only statistics. So like it's only using some statistic methods. But when you're using the facies model, when you input the porosity values into the facies model, it will adjust the values of porosity from my analysis. So let's say that based on these 2 wells, this area should have a porosity as high as 30%. But then from the facies model, it turns out that area is composed of tight shale stone or something that might not have that much of a porosity. So it kind of adjusts the value down and makes it way more realistic, makes the porosity distribution more realistic because of the facies model. And of course, if you have the logs, if you have the core data, you can do the core flooding experiment to plot the relationship within the porosity and permeability, and just use the formula that you got from the relationship to transform the porosity to permeability. But there are also so many literatures out there that you can use for to calculate to transform the porosity to permeability. The key is just to experiment as much as you can, like just calculate them all. It's pretty easy. If it can also be used in Python to just like experiment with which formula that would work for your permeability model. And so there's this study from one of my college from UT Austin. So there's actually a relationship between the methods on how detailed your modeling is and your estimated storage capacity and your refinement. And also it might, in a glance, it sounds like it's a bad thing that the more detailed your modeling is, the less estimated storage capacity that you get. But actually it's a good thing, because we cannot be so sure. And I personally think it's dangerous if you overestimate your storage capacity, because it will have something to do with injectivity, with how much you will inject to the reservoir. And it could, if you are overestimating it, and it's just like you're putting something that cannot contain what you're gonna put, and it can lead to like lots of bad things. So the main point is to, like, if you have a good data and if you can have access to as much of a data that you can, just utilize everything. And of course it will be costly too, but again, when it comes to like academic projects, there's so many. I'm speaking from experience. When it comes to academic projects, we have like some kind of freedoms to like get as much data as we want. But like in industry wise, there's some limitation in the cost. So it's just good to know that if we have, let's say that we don't have that much data, our data is not that detailed, and we have this much of a storage capacity, it's wise for us to acknowledge that and to say that it might not be our maximum capacity, and we might to like adjust it down just so that we do not overestimate them. And so let's say we have the model ready, we ready to run it into the simulation, and we also calculated the static capacity, but we don't know like how much injection is too much. Like what if 1 million tons of injection per year is too much, or like what if that is too fast, or like what if it's too low, what if it's too little that we can actually inject more and to maximize them, because we want the CO2 concentration in the atmosphere to be to lower down as fast as we can, because we're dealing with time when it comes to climate change. And so when it comes to injectivity and dynamic capacity calculation, it has a lot to do with efficiency factor. And as you can see from the formula here, I don't want to ruin your Saturday with formulas, but I just want to point out that it has a lot to do with pressure buildup. And pressure buildup, as I told you earlier, when it comes to like determining the window for CO2 storage, has something to do. The lower boundary for that is the overpressure. So we don't want to reach that pressure, and so we can calculate that and like calculate the efficiency factor. And one of the examples for efficiency factors over here is from a study from the Lawrence Livermore National Lab. So this is the formation target for CO2 storage in California. And so just a little bit of information, maybe someone already knows about this. California is really seismically active, and the geothermal gradient is basically in some areas are higher in some areas compared to Texas. And so even in some area, the geothermal gradient is not linear, the pressure gradient is not linear. And so you can see that they're being very moderate about the efficiency factor that also it has something to do with the pressure buildup as well. So they only have a range of 1% to 4% for the efficiency factor. But again, it's different from one geology to another, like for this one. So this one, again, from the same study that I showed earlier about the calculating the capacity storage, and has something to do with the cost and the lower capacity. And so this is from study in the Gulf of Mexico, and because of the geology, it has like a range of efficiency factor as that can be up to a little bit over than 40%. So yeah, it varies from one geology to another. And let's say that we have this much dynamic capacity, so we can inject the CO2 as much as we can. So would it be better to like install multiple wells in one area? Would it even increase, would putting more well could increase injectivity of injecting the CO2 into the subsurface? But one of my experience says no. So what is shown over here is basically we're doing an experiment in injecting as much as 60 million tons of CO2 with one well, and it matched. We can store 60 million tons of CO2 in one wells. But when we add more wells, as much as 4 wells now we have 4 wells, but the capacity does not increase as much, only 60.8 million tons of CO2. So the injectivity for each well actually decreased from 60 million tons per well to only 15.2 per wells. And we don't want that, because wells are expensive, and what's the point of spending more money if we can only store that much of CO2, not that much more of CO2. So yeah, I think that's all I have. The next couple slides are about my projects that I can share. Because I can't share the projects that I'm currently doing with Tetra Tech, because all of the information are confidential. But I hope you guys can still learn something out of it. And so the first one is from my thesis. So as I said earlier, also, as Aditya mentioned, I used to work in oil and gas, and so I'm pretty familiar with lots of oil and gas concepts. And one of the interesting concepts that I applied for this study is the oil migration concept. So this is an SPE event, so I'm pretty sure everyone's familiar with the concept of source rock and reservoir. And so usually when the oil migrates from the source to reservoir, there would be some fraction of the oil that would be lost in the migration, in the carrier bed, and we call it a migration loss. And so I'm using that concept and apply it into CO2 storage. So the experiment is to inject the CO2 at this injection point that's really close to the anticline, and it's usually like a sweet spot for us to inject water or any kind of fluids that we use for tertiary recovery for oil and gas development. And the other one is to inject the CO2 at the base of the syncline that is analogous to the source rock in petroleum system. And it shows that when we're injecting the CO2 at the base of the syncline, the CO2 barely reach the anticline. So blue means no CO2, red means 50% of gas saturation, of CO2 saturation. So you can see that this is 30 years. So we're doing 30 years continuous injection, where we inject like 1 million tons of CO2 every year. So it's a total of 30 million tons of CO2 injected, and they do not reach the anticline at all at the end of the injection. But you can see some area are occupied some areas have like 50% of gas saturation, but I think this is 30 years after the injection stops. So we can see some of the CO2 still migrates and barely reach the end decline, but you can barely see any part of the plume that has 50% of gas saturation. I think it's mostly less than 30% of gas saturation. So we can say that the CO2 is stabilizing, settling for good. We can also say that the CO2 is immobile because of the lower gas saturation than before. But when we're injecting the CO2 into the anticline, that is the base case, the plume does not differ that much. I mean, in terms of size, it doesn't differ as much from right after the injection stops to 30 years after the injection stops. But you see that there are still lots of area that has 50% of gas saturation, which means that it could still be in a free phase CO2, and that we can probably say that most of the CO2 in here, they already go through residual trapping and even go through the solubility trapping, which would be much more stable, much more permanent compared to this that might still be in the phase of structural trapping. And aside from that, we also measure the average reservoir pressure from before the injection, throughout the injection, and after the injection. So just because this is a really small image, I just want to point out the red one is for the base scenario. So it has the highest pressure increase, and it takes longer for it to reach pressure stabilization. Meanwhile, the green one over here is the case where we inject the CO2 at the base of the syncline. So the pressure does not increase that much, but and also it takes like much shorter for it to reach the pressure stabilization. That is the when the pressure does not change as much, and it's really close to the pressure, the value of the pressure before the injection. The next project that I'm sharing is from my work with the Lawrence Livermore National Lab. And so the initial idea is to utilize oil and gas, gas depleted gas fields in Northern California basin. I think it's Northern Sacramento Basin. And we gathered these 5 neighboring gas fields, and we see that most of the gas fields are like most of the gas comes from like distant formations within this like overall formations. And I think the number that we got is around, if we utilize every gas fields in here, just the gas reservoirs, we can only store as much as 7 million tons of CO2. But we utilize more data throughout the area, throughout all of these areas, and it turns out that we can store as much as, I think, 90 million tons of CO2. And so yeah, the point is to, injecting it into permeable formations and make sure that we also have the impermeable formations that will cap the CO2, that will keep the CO2 in the underground. I think that's all I have for now, for today. I think I sent the slide to Fikri. So if anyone wants to get to know about CO2 storage, you can read it from here. This is a very good start for you to get to know CO2 storage. I think I also mentioned in here, this is a work from Lawrence Livermore National Lab about how to get California into carbon neutral by 2040, I think. It's a really thorough assessment, and you can also see it's not only CO2 storage, but they also cover natural solutions such as reforestation. So it's a really good thing to know that we're not only working like CO2 removal is there's no bullet points in CO2 removal and especially in climate change. I think that's all I have for now, and I'm happy to answer any questions that you have. Thank you.
Thank you very much for your presentation. It was really nice, and like I don't know more than half of the stuff which was present there. So yes. Yeah. Any questions from anybody? Maybe Fikri. You can go first. You just raise your hand.
I'm just clapping, but yeah, I
Okay.
have as well. There's such a interesting presentation. Melianna, I have question. So do you think the CCS depends on oil price? I mean, is it such a good decision to perform CCS in EOR scenario when the oil price is low?
Yes and no. So I think I can say that 60% of the answer will be yes, because again, it has a really close relationship with oil and gas. And in EOR, even though you do not really store CO2 that much, but we get help a lot from that operation, from the pipeline that's being built. Because the biggest cost of CO2 storage is not actually the storage part. So like the biggest cost of CO2 storage is actually from the capture and also from the pipeline. And so if such technology already exists to support other operations such as EOR, and that is mostly being operated by oil and gas industry, it would be really helpful to like bridge our way to sequester the CO2 permanently, because we already have the pipeline. It would bring much less cost. I don't know what the policy is in the Germany, but in the US, we have carbon tax for CO2 storage operation. So they basically put a price on CO2 for EOR or for oil and gas related, not just oil and gas, but like if you're using the CO2 or it had something to do with like other operations, the price of your CO2 is around $25 per ton. But if you're sequestering the CO2 for good permanently, the price is about $50 per ton, and I think they are planning to increase the price, and that's why lots of proposals are being submitted to the government to like accept the drilling permit, etc. And so, yeah, yes, because of the close ties of the oil and gas industry, and we can benefit from all of the facilities that they built for the EOR if they are in a good business with the high oil price, but not necessarily if we already have like everything being built helped by them, because at least in the US, it's not just driven by oil price, but also because of the carbon tax.
All right, thank you.
Yeah, Ryan, please go on.
Yeah, thank you, Melianna, for the presentation. I would like to ask a question. You mentioned several aspects that we can consider to make sure that this place is kind of potential, like technical aspect or geological aspect, or even how safe the place itself. I mean, like for geological, you said also that basalt rock is kind of like much faster to be processed for the CO2. So can you make some kind of like list of like, how can I say, one of the most important aspect that we have to consider as a geologist or a geoscientist here, or even at least make the list of priority about what kind of aspects that we have to consider that the area can be a potential area for the carbon capture storage itself. Thank you.
As a geoscientist, for sure it's data. So the more data that you can, the more detailed assessment that you make. And as I think I did not really make that clear. So in here, as we can see that when it comes to reservoir quality in the anticline geology wise, and compared to like this kind of area, which is usually a carrier bed, and usually the carrier bed is more heterogeneous. What it means by heterogeneous is just that it's not only composed by sandstone, but also has some other kinds of rock as well, just such as shale or like lamination of shale or siltstone. But like but like the anticline, it's mostly based on like mostly just sandstone, and so it's more homogeneous, and so it's easier for the CO2 to like migrate. But like the thing is with like homogeneous reservoir, the only good thing that we can have is that the plume area, that is the CO2 distribution, will not be as big as if we're injecting the CO2 at the carrier bed. But like in carrier bed, as you can see, even though the plume size is bigger, the stabilization is faster, so it's safer. And also it has, like, if you can see some space in here, so it means that even the reservoir itself limit the vertical migration of the CO2 compared to when you inject the CO2 very close to the anticline, that's like the conventional reservoir. And so I can say that we actually can just store CO2 anywhere. There's so many options to store CO2, but of course, as a geoscientist, data is very important. Again, because of that, but we also have to like consider the window itself, like the window between the supercritical and the overpressure. That's like the main thing to consider when we are about to inject CO2 in a sedimentary basins. But for carbon mineralization, we call it carbon mineralization usually for injecting the CO2 into basalt. I mean, for that kind of sequestration, they usually call it carbon mineralization. Not really familiar with that, but I think it has something to do with like you need to like closely study the chemical reaction between the CO2 and the basalt, and again calculating the capacity, how much CO2 can you inject, how fast can you sequester the CO2. There's also another methods that I recently learned about related to carbon mineralization. It's using ultramafic rocks such as serpentinite to sequester CO2, and lots of universities are working with mining companies to do such experiments. So basically they're using, you know, the rocks from the residue of their mining operations such as serpentinite. They break it up into like certain range of sizes, and just spread it on the ground, and the CO2 will be captured by them. So yeah, when it comes to CO2 storage, there's so many things that we can do. We can basically sequester carbon anywhere, but as a geoscientist, the most important for us is data. But when it comes to business, the most important thing in carbon storage is the distance between the sink and the source, because there are also some policy about that regarding, at least in the US, regarding the carbon tax. Like the distance should be like less than, I think, 10 or 15 miles or something like that. And yeah, it depends on which perspective you are seeing the carbon sequestration. But for geoscientists and engineers, it's data. And if it's sedimentary basins, it's always good to consider the sequestration window first. That is the overpressure and the supercritical window, because it's different from one geology to another.
Yep, makes sense. Thank you so much.
I have a question actually. Like we store the CO2 and everything in the ground, but from a social point of view, or like from a responsibility point of view, it makes sense. But from commercial point of view, how does it make sense? Because at the end of the day, we are just storing the carbon dioxide inside the ground, and it's either it's either turned to stone, or it's either left there. But what do we do with the carbon dioxide which is stored there? Like, how does a company which does carbon capture and storage profit from this whole operation?
So the first carbon capture and storage for permanent sequestration project ever is being carried out by Statoil, now Equinor in Norway, the Sleipner project, and their main consideration to do so is actually because of the economical reasons, believe it or not. And it's because in Norway, there is a certain policy that if there's like a carbon tax or carbon cap or something, and so they calculate, they found this Sleipner project, and the concentration of the CO2 is really high. And so if they are producing the gas from that field and they just fed the CO2 into the atmosphere, they are gonna pay so much money for the tax annually. And it turns out that if they are sequestering the CO2 instead, it's like the money that they have to pay for like funding the project is much less than paying the tax in a long time throughout the project. So in terms of profit, I can't say about other countries, but the main drivers for now in the US at least is the carbon tax that I mentioned earlier, the $25 for EOR and the $50 for permanent sequestration. But I think what I can learn from that is that well, everything comes to like when like everything comes back to economy, and if that's the reason, if that's the reason how the first CO2 sequestration happened, I don't think such scenario will happen in the future that will make corporations to do these things that might not seem economical, but will save them lots of money in the future for like other consequences, such as carbon tax that they're going to face in the future.
Okay, makes sense. Thank
That's
you
like
very much.
basically preventing you from paying so much money in the future. Because like, you know, we all have this, what's the name? Discount rates or like inflation. So the amount of money that you're gonna spend in the future will be like much more than the amount of money that you're spending now. So might as well just spend the money now for like future investment.
But at the same time, there the countries like Norway and let's say Germany has a tax, and US has some tax, but these are smaller in number, right? The energy usage by these countries are really low compared to Asian countries like India or China. So the main purpose of doing this is to control the climate change and everything. But at the same time, how would this be effective if the other countries are not taken into, let's say, consideration? Is not the correct word, but yes, yeah. How?
Here's how the number tricks you. It's true that the emission of the US and Europe is lower compared to India and China, and it is. But if you take a look at the per capita emission, US is the highest. Can you imagine? There's only like 320 US. I think from my last energy law class, I think the total citizens of US, or like the total, well, let's say in the US there are 400 million people in the US, and in China and India there are like, I think 1.2 billions of people in China, and a little bit less of that in India. So it's like twice, 3 times of people, but like the amount, the emission is not that much of a difference. So you can see that the per capita energy is so much higher in the US. And it has something to do with the technology as well when it comes to climate change. This is what I keep saying to everyone. Just do what you can, because in the US we have the access to do it, we have the resources to do it, we have such investment, we have such policy to do this thing, and so that's why we can do it. And it doesn't matter what China and India do, it matters what we do. Maybe China or India has their own strategy, and I also believe there are lots of countries out there that do some collaborative effort for that. Just like if you know, there's this country called Trinidad and Tobago. It's not a big country, but they have a CO2 storage project in there, and it's because I think it's a project from BP. But yeah, even that small country can do such a thing. So I believe with like collaboration, we can all work together for that. And like the thing is that we can't control what other people are doing, and like we can do carbon sequestration here, and it's still pretty hard to do it here because of the such regulation. But like if we can show that we can do it, and like it's like we're doing all the research to minimize the cost, and so we develop we develop everything until finally the cost goes down, and so other country can benefit from that. It's just like solar panels. Solar panels used to be very, very expensive back in early 2000s, but because we keep doing all the experiments to bring the price down, other country can benefit from purchasing the solar panel in a much less price compared to when it just shows. So it's just like that. We come from the disruptions we do the sacrifice because our per capita emission is so high, and so we have this responsibility to give back to other people who can't do as much as we can do.
Yes. Okay. Thank you very much. Yes, it makes sense. Yes. Thanks. Anybody else wants to ask a question? Yeah, Ryan, go on.
Okay. Please excuse me to talk a bit about the pressure building actually. So I cannot really connect it into the dot of here. I mean, like I got the idea of your results here in the point 3, faster pressure stabilization at synchronous scenario. It will be like easier, stabler than the best scenario. I mean, like what is the relationship between the pressure building and also the synchronous itself? I mean, like it has to do something right with building, and how do you explain pressure building as a geoscientist and not
so it has something to do with the CO2 saturation in here, and between the two of them, I think this is the 60 million tons of CO2. But yeah, anyway, we inject the CO2 same amount, but just different placement of well. Same geologic model, but just different placement of the well. And from the simulation results and also from my fluid flow analysis is that when you're injecting the CO2 into a structure that resembles a carrier bed, there's the CO2 cannot move as fast as when you're injecting the CO2 in a homogeneous reservoir. Because like in homogeneous reservoir, it's just so easy for them to like keep moving because of the lower capillary pressure that they have to pass through. But over a long time, the more you inject, the CO2 just kind of makes like a big layer of CO2 on top of there with lots of with pretty high gas saturation. 50% is pretty high gas saturation when it comes to CO2 storage. And so what we see in here is just that the CO2 trying to keep on moving, but they cannot breach into this permeable layer. So the capillary pressure is still there because they're still trying to pass through this layer that is the lower permeable on top of the reservoir. The capillary pressure is still there, and it stays there even after the injection ends, and it takes a while for them to stays down until so the injection stops and there's no more support, no more incoming CO2 into there, so they can stay there, but it takes longer because there's still capillary pressure on top of there. But in this scenario, you're injecting the CO2 into the sandstone that also has like some siltstone into it. So you can see that the nature of the CO2 to move is buoyancy. The main force is the buoyancy. So it's just CO2 nature to like, especially we're injecting them into a brine that's water, and they even though the density the density is pretty close, but it's still much less compared to the brine. So it's just their nature to keep on migrating vertically, but because there are some shales in between the sandstone, so they have to move laterally first before they can find any structure or like any pore space that they can go through with the adequate capillary pressure. And because of the lateral migration, the CO2 went through this, where's my mouse? The residual trapping phase a lot, and so they stabilize faster, and so they're not much of a CO2 that tries to break the capillary the impermeable layer on top of the reservoir, and that's how the pressure is much less. So again, this is an average reservoir pressure. If we calculate, if we do a measurement of just a pressure in one point during the injection, it is actually higher in like the Sinclair scenario because of the heterogeneity, because some of the CO2 they just get out of the well and they expect to like go flow through the sandstone, but they meet some shales and their paths are blocked, and so the capillary pressure is much higher. But then over the time they go through residual trapping, so like it stabilizes faster and it doesn't accumulate on top of the anticline like that.
Yeah, thank you. It's pretty interesting that CO2 has kind of like special ability or special characteristic to be stabilized and stuff. But yeah, thank you so much for the explanation.
It's about the interaction.
Yeah,
the interaction.
Even if we face a different lithology, it will be like different.
It's different. Yeah. What I'm trying to show in here is that I keep saying that this is the same model. This is the same rock. It's the same target. You're targeting the anticline, but just the one thing, but like the other scenario is that we're injecting them strategic enough to not populate the target too much. So can make such a difference.
Yep. Thank you for the explanation.
Yeah, Fikri, please go on.
Yeah, thank you. I have other question. Is it possible to perform carbon capture storage in a collaboration with geothermal exploration?
Yeah, for sure. I think what Carfix is doing is to mitigate the emissions that they, as funny as it sounds like, geothermal actually produce greenhouse gas because CO2 is greenhouse gas. CO2, water vapor is CO2, and CO2 is a greenhouse gas. And I'm applauding them for their responsibility, showing that we have to be responsible for everything that we do, and like they really are trying to produce energy as clean as possible. And one thing that I know of CO2 storage and geothermal is to inject the CO2 into this reservoir that have pretty high geothermal gradient. And so by injecting the CO2, you will drive the pressure high, and there's another well for you to like drive the energy. So this has something to do with the exergy concept. So exergy is basically the amount of the energy that the amount of energy that you produce from like using energy as well. And so it's just like a two-edged sword, I can say. So let's say you're injecting the CO2 and you see that it's so fast for the pressure to dissipate. And so we don't have to worry about it. But when you find a geologic area where you store the CO2 and the pressure builds up, I mean, the pressure drives like other energy. So pressure itself is an energy. So why not just extract the energy? So it's basically extracting the surplus of the energy that you create by injecting the CO2. But I think we have to be very careful about that, because lots of areas with high geothermal gradient are located in a seismically active area, just like in California. And I think in Indonesia, they're trying to do it in Natuna, and they have a pretty high geothermal gradient over there. I'm not sure how much geomechanical approach and mitigation that they have to do, but I can say it's doable just because of the concept of the exergy that they're basing it into, that you inject CO2, it increases the pressure. So you just can harvest the pressure back and turn it into energy. So yeah.
Really nice. Thank you for the insight.
I think we have we answered most of the questions. So last time, does anybody have any more questions? Maybe. Okay, then if you all are comfortable, maybe we can have a small photo on Zoom so that we can use the photo on our new SP website, which is being created by Aska. So yeah, we also have to thank her a lot because she puts in more time for the website. So yes. Yeah. Okay. Okay, thank you very much. That's all. But yeah. Yeah, thank you very much for presentation again, and we really appreciate that you have come to here to give your time and everything, and it's a lot more informative than I thought at least. So yeah, it's a lot more deep and everything. So yes, thank you.
I think we should have a photograph first before leave. A photograph, yeah. So okay, maybe I'll take the screenshot of it. Yeah.
Sure.
3, 2, 1. Okay, one more. 3, 2, 1. Yeah. Yeah. Thank you, Melianna.
Thanks for having me. I hope I'm not rambling too much, and I hope you guys learn at least something from this talk. So yeah.
Yes.
Bye. Have a good weekend.
Bye.
Bye.
Yeah,
Thank you.
Thank you.
Bye. Thank you.
So the next speaker is Aksita Kanwal.
What?
Oh my goodness.